Welcome to Skill Science Academy. Imagine you are an instructional director tracking exam scores for a large student cohort. You plot each score on a timeline, but as hundreds of students submit their exams, a critical data problem emerges. The data points begin to overlap, hiding individual results. With multiple students scoring exactly 80 or 85, those duplicate results physically hide behind each other on a one-dimensional line. This masks the true density of your dataset, a fundamental challenge of raw, unorganized information that prevents us from seeing the actual business reality. To reveal those hidden measurements, our initial instinct might be to stack identical scores vertically. While this elevates the points along the y-axis to show volume, this method is mathematically fragile and inefficient for large datasets. Achieving the exact same score is rare, meaning pure stacking leaves us with thin, isolated towers, separated by massive, empty gaps. Since a 79 and 81 are practically identical in performance, this method fails to give us a cohesive picture of the overall student trend. Data science uses a smarter approach called binning. We divide the range of values into equal, fixed intervals, such as 10-point scoring brackets. Every student score falling within a bracket is stacked into the same continuous column, regardless of their precise individual number. This transforms chaotic data into clean, segmented data pillars. The taller the pillar, the higher the frequency of students in that bracket. This is the birth of the histogram, a tool that instantly maps data density, concentration, and structural flow. Once your histogram is stabilized, you unlock the power of predictive probability. By observing the shape of our segmented pillars, we can map a continuous statistical curve over the data, creating a stylized data mountain range. In this case, student scores form a normal distribution, peaking in the 80 to 90 bracket and sloping symmetrically. With this visual proof, we can confidently predict that the next student to submit an exam is highly likely to score within that central peak. Conversely, scores on the extreme outer tails are rare. The histogram acts as the graphical justification that allows data scientists to use these idealized distributions to successfully forecast future real-world outcomes. Business reality isn't always a perfect bell curve. If we look at an elite, highly rigorous certification exam, the data shapeshifts drastically, requiring a different approach. A massive cluster of students scores at the lower end, with frequency dropping off sharply as scores increase. We map this continuous decay using an exponential distribution, which serves as our new analytical baseline. Knowing the baseline decay rate allows us to predict the rarity of high-performing outliers in future cycles. Always ensure your distribution model mirrors the physical reality of the process you are measuring. We also face a critical decision regarding bin width. If we make our bins too narrow, like using 1-point microintervals, we destroy the utility of the histogram and revert to the problem of scattered, unreadable data. In machine learning, this is called overfitting. We capture every tiny fluctuation and noise in the data, but fail to see the broader trend. This fragmented view provides no actionable insight to our instructional team. Conversely, if we make bins too wide, we fall into the trap of underfitting. This aggressively aggregates data into a crude binary view that fails to reveal the nuanced reality of our student performance. When bins become ultra-wide, they behave like a blunt instrument. We erase the nuanced peaks and subtle student clustering, losing the organic curve of the performance landscape. Remember, good analytics always requires a careful balance between simplicity and detail. The ultimate lesson in crafting robust data visualizations is that finding the optimal bin width is an iterative, experimental process. You can't blindly trust the default output settings of your programming library or analytical software. Finding the analytical sweet spot requires you to manually adjust intervals until the structural picture becomes crystalline, where noise is smoothed out, but true statistical patterns remain visible. This ensures your logic is built on the most accurate visual representation possible. Please watch the interactive sandbox just below this video to experience live learning and toggle the buttons. Remember, every small insight is a step toward mastery. Thanks for watching this video. Keep upgrading your skills scientifically with Skill Science Academy. I'll see you in the next level.